Yeah, so please, microphones off unless you have a question. Danylo, please, whenever you're ready.
Okay. So let me start. Okay. Just tell me if you see my screen.
I see your
Yes.
screen.
Very good. So then I can begin. So yesterday I was going a bit fast. Today I'm going to try to go slower. And also please, well, if you have any questions during the talk, please feel free to interrupt me. And maybe if you also think I'm going too fast, you can also tell me that. Okay, so I'm going to start from scratch. So none of the things that you saw yesterday will be, well, the things will reappear, but I won't refer to them as already known. So let's look a bit more closer at the notion of modular forms for the group SL2Z. So the transformation law, as I wrote it out yesterday, is, well, as written here. So for any matrix with determinant 1 with integer entries a, b, c, d, you're interested in functions which transform in this way when you change the variable to this fractional linear transformation. So one thing one immediately notices is because we allow all matrices of determinant 1, there's one matrix, namely minus identity, which is in SL2Z, which acts trivially on the variable, but this factor here, c tau plus d to the power k, it negates. So actually, if you look at the definition, it just says that f of tau is equal to minus f of tau. And because of that reason, all of them will vanish. So for the purposes of this talk, and well, okay. I mean, for the purposes of the talk, we'll just concentrate on the case when k is even. There is a way to make an interesting notion of odd weight modular forms, but it's not this way. One has to introduce some kind of multiplier system here. So because in the case of k even, this factor is invariant under the negation of the matrix. We're actually talking about the action of this group PSL2Z, not SL2Z. And one can see that the action, the fractional linear transformation is invariant under multiplication by minus identity. So we're not losing anything. Okay, so just to recall, the group PSL to R acts on the upper half plane on the left, and this is actually the full group of biholomorphic automorphisms. And in particular, using this action, we can also define the action of the same group on the functions. And we do it in the, well, actually, it's an infinite family of actions. So one depends on the weight k. And we define it as follows. So we have this slash operator. So f slash with index k, and gamma is an element of the group PSL2R. And we just define it to be the value of f at the left action of the group multiplied by this so-called automorphic factor. And first, so yesterday I didn't give any exercises. Today there will be quite a few. So first exercise is very simple. It's just to verify that this is indeed the right action. So one needs to verify if you take product of two matrices and you act by it in weight k, then it's the same as acting by one of them and then by the other. Okay. So now the transformation law that we require is simply the action of this slash operator in weight k on the function f is equal to the f itself. And so this should hold for all elements of the group PSL2Z. But since, because of the exercise on the previous slides, you know that if this identity holds for two elements, gamma 1 and gamma 2, it also holds for their product. Okay. So in principle, we only need to check this for the set of generators of the group, which is exactly what we'll describe now. So we know these special matrices in PSL2Z. Well, okay, I'm abusing notation slightly. So I'm still writing matrices, but I'm actually talking about the equivalence classes modulo multiplication by plus minus identity. but hopefully that won't create too much confusion. So we introduce these two elements. So one is the matrix 0, 1, minus 1, 0, and the other is the matrix 1, 1, 0, 1. So if you look at the action on the upper half plane, this corresponds to shift by 1, and this corresponds to the inversion. So it's a map that sends tau to minus 1 over tau. And now the second exercise is again not very hard, is to show that the group PSL2Z is generated by these two elements. And not only that, they actually satisfy certain relations. So S square, if you apply this inversion twice, you get the identity. And if you take one of them and then the other, and you apply this composition 3 times, you also get the identity. And again, here I'm talking about the elements of PSL2Z. So if you work with SL2Z instead, S square would be minus identity. Also for the exercise, you don't have to show that these are all the relations. That would be a little bit more complicated. But for our purposes, this implies that we actually have to check only 2 transformation laws to show that something is a modular form for SL2Z. We need to verify that it's invariant under S and under T. Now the T is it's special. So as I said before, T is just translation by 1. So the condition that F slash KT is equal to F is just saying that F is a one periodic function. Now there is a very nice simple result about one periodic functions, which is essentially, I mean, it's a result in complex analysis talking about Laurent extensions, but written in a different coordinate. So any one periodic function, as long as it's holomorphic in the whole upper half plane, can be developed into a Laurent series. So it has possibly infinitely many terms which have negative powers of Q, which if you look, I mean, the difference between positive and negative powers of Q is that the positive powers are exponentially small at infinity because we're only looking at 1/2, like we're only looking at the upper half plane. But the negative powers of Q are exploding, so they're exponentially growing at infinity. So they do behave quite differently, but in any case, we can always develop this thing by the general principle of Laurent expansion. And so I will recall now, well, not recalling, I mean, this is the first time you're seeing this essentially. So a modular form of weight K for the group gamma 1 is an analytic function F on the upper half plane such that first it satisfies the transformation laws F. So the action of the slash operator preserves F for all elements of the group, which from the previous slide, you know, you only have to check it for 2 elements, S and T. And the second condition is that because it's, well, T invariant, it has this Laurent series expansion, and we require that no negative powers of Q appear in this expansion. Okay. So, and in particular, there's an important class of modular forms where we have a stronger condition, which is first, the constant term of the expansion also has to vanish. In that case, we call it a cusp form. So, and we use this notation for the spaces of modular forms and cusp forms. So what I mean is the set of all such things is actually a C vector space, as one can easily see from the definition. And so, okay. So just to make some detour, I won't talk very much about the theory for other subgroups other than the full modular group, except maybe for the principal congruent subgroup module 2. But in any case, the definition is very easy. You just have to, I mean, one part of the definition is more or less trivial. So you just require the transformation law only for a subset of elements of the group. So you just require, so for a modular form to be modular form of weight K for the group gamma, you require it to be invariant under all elements of gamma under the slash operator in weight K. And you require that the function, if you apply any element gamma from the full group PSL2Z to the function, you again get a you get a holomorphic function on the upper half plane. And one can show that if gamma is a subgroup of finite index, this is actually has a Q expansion, but not necessarily in powers of Q, but in powers of some fixed power of Q. But actually, well, this part is not necessarily important. We just require that this thing is bounded when tau goes to infinity. And we require this for all elements of PSL2Z. And similarly, cusp form now is a bit more complicated to define, but basically you just require the vanishing of the constant term for each of these expansions. So for each element gamma in PSL2Z, you want this slash f slash gamma to have no constant term in the Fourier expansion at infinity. Okay, so there's some more geometric way of viewing this, but since I'm not going to talk much about other groups, I'll probably skip it. So again, the notation from the previous slide, we're just, I mean, we use the same notation, except we change the parameter from gamma 1, by which I have denoted PSL2Z, to the group gamma. And yeah, so one thing that I haven't mentioned in the first talk, well, I have mentioned it, but it didn't really go into it. So the set of all modular forms of all non-negative weights is actually a ring, because, well, the condition that you need to check that f slash k gamma is equal to f. If you multiply two such things in weight, a modular form of weight k and a modular form of weight L, then one can actually check that this condition will be preserved, except you have to slash in weight k plus L. So the product of two things in weight k and L is a modular form of weight k plus L. So if you take this direct sum of all these vector spaces, which it really is a direct sum, because there are no, I mean, maybe it's a simple exercise to show that there are no linear relations between modular forms of different weight. It's a simple, very simple exercise. So this direct sum, because of the fact that you multiply things, you get again a modular form. This is actually a graded ring. Okay, and we'll come back to it for the, well, we will actually describe the structure of this ring for the full modular group later. Okay, so from the condition that the modular form satisfies this transformation law, we see that whenever we have 2 points in the upper half plane, which are equivalent under the group gamma 1, so there's some element of the group that sends one point to the other, then the values at these points are related. They're not necessarily equal, but they differ by something rather elementary. So in particular, it's useful to know like what is the set of representatives for all such gamma 1 orbits. So with like a canonical representative for each one. And this is accomplished by the notion of the fundamental domain, well, with some small caveat. So fundamental domain is an open set such that its closure contains all representatives. So it contains, it intersects all gamma 1 orbits, but its interior, well, the set itself doesn't have any two, so no 2 points of the set are equivalent under gamma 1. Okay. And so for SL2Z, this is a famous picture that probably many of you saw before. This fundamental domain is easy to describe, and it's given by the set of points which are in the strip between -1/2 and 1/2, and which have absolute value greater than 1. Of course, in the upper half plane. So, and then the picture that you've probably seen before is this thing. So here I have noted 2 points of interest. So I is just the square root of -1, and rho is a cubic root of unity. So these 2 points play somehow a different special role, which we'll explain a bit later. And just to indicate the proof of the fact that it is a fundamental domain, I won't go into details, but maybe if you want to work out, this is a nice exercise. So first thing is you use this identity, which is easy to verify directly. And this shows you that, well, if you take any point tau in the upper half plane and you look at its gamma 1 orbit, then the imaginary parts of this orbit are actually, well, they have a very simple description. It's just the imaginary part of the original point divided by square lengths of some point in some lattice. So because C tau plus D is a point in the lattice generated by tau and 1. And we know that lattices, they don't have many short vectors. In particular, there's only finitely many vectors which have lengths less than 1. And so because of this, we can find at least one element in the orbit which has the largest imaginary part. It may not necessarily be unique, but there certainly is a well-defined maximum. So it's not just a supremum of all imaginary parts. Okay, and now the claim is, well, this tau prime, the element with the largest imaginary part, it has to be almost in the fundamental domain already, except, well, if you translate it by 1 in any direction, the imaginary part doesn't change. So, sorry, here I'm just explaining what I said before. But now if you translate sufficiently many times to the left or to the right, you can assume that this point tau prime is actually in the strip between -1/2 and 1/2, maybe including one of the two. And again, since we know that tau prime has a maximal imaginary part among the whole orbit, we must necessarily have this inequality as well, because otherwise, if you apply the S element, you get a strict inequality here. So this shows the first part, that any orbit, and the gamma-1 orbit of any point in H intersects the closure of F. And the second part is actually also not very hard, but I leave it as an exercise. So once again, one can use this identity the proof is not hard, so maybe I won't say much about it. Okay, so now that we have the fundamental domain, maybe this picture will give you some intuition of how this looks, even though it's very complicated. I mean, the picture gets more and more complicated the closer to the real line you go. But at least the first few iterates, you can see here how they're distributed. So here, for each copy of this domain, I put an element of the group gamma, which maps the original fundamental domain to this tile. So for example, here it's the original fundamental domain, here it's translated by 1, here it's inverted, and so on. Okay. So as I've said before, there are these special points I and rho, and the reason why they're special is actually they have a non-trivial stabilizer in the group. So the element S, the inversion, you can easily see that it fixes the square root of -1. And this product U, so you first apply the translation by 1 and then you invert, it fixes the third root of unity rho. And in fact, one can prove, and this is not very hard. So these points are called elliptic. This is just the definition. If a point has a non-trivial stabilizer in PSL to Z. But one can actually prove that up to the action of the group itself, there's only 2 elliptic points. So what I mean to say is that under PSL to Z equivalence, any elliptic point is equivalent to either I or to rho. And of course, these 2 points are not equivalent. So this is an exercise, but because of so these points usually one has to treat them slightly differently. So it's convenient to introduce a kind of measure of how bad the point is from being regular. And we define it to be 3 for the orbit of rho, and 2 to be for the orbit of I. I mean, the definition of NZ without a non-explicit definition would be just the order of the stabilizer in PSL to Z. Okay, so now we come to an important part. So we want to prove finite dimensionality of the space of modular forms. And for that, actually, there's a kind of a formula for the total number of zeros of F in the upper half plane when you look modulo the gamma-1 equivalence. And that formula, so first of all, I have to say a little bit. So we can define the usual order of vanishing of F at any given point. And I mean, it makes sense, except, well, we want to talk about the order of vanishing at the orbit. But because the transformation law for the modular form involves this factor c tau plus d to the power k, it's easy to see that this thing doesn't vanish anywhere in the upper half plane. So it means that if you change your point z by an element equivalent to it, the definition of the order, I mean, the order remains the same. So it's actually well defined on the full orbit, including the points I and ρ. And for infinity, we can also define the order of vanishing, which is just the smallest coefficient which is non-zero in the Q expansion. So it's kind of the order of vanishing in the Q variable at 0. So in that sense, we have the following formula, which is going to be the key for the proof of, well, for one of the proofs of finite dimensionality. So if you now take any non-zero modular form of weight k, well, I should have written PSL to Z here, then the sum of over all, well, I mean, the sum here is over all points, but actually there's only finitely many zeros up to equivalence. So the sum over all equivalence classes of zeros of F of the order of 0 divided by this the size of automorphism group, so the stabilizer, plus the order of at infinity of F is actually independent of the form. It's a constant that depends only on the weight. So it's k over 12. And I won't say much about the proof, except I'll indicate the main idea, but it's some exercise. So what you do is you just compute the integral of d log f, which would count you the number of zeros in the usual way, but you integrate it over certain Swiss, I call it a Swiss cheese contour, which I'll show in the next slide. And then you compute that various parts of this contour contribute more or less all the terms in this formula. They add up to 0 because of the theorem of Cauchy. So the contour of integration is given in this picture. So what happens here is we take the fundamental domain, we cut it at some height, sufficiently large height, such that there are no zeros higher than that. We cut out all the possible zeros inside this domain, all the zeros of F which are inside. So we pick some small epsilon neighborhood of each one. And we also remove epsilon neighborhoods of the elliptic points. And then one can show that, well, all the interior points contribute just the order of, once you integrate it with the right orientation, these things contribute the order of vanishing at each of the regular points. This integral up to something which is small with epsilon contributes the order of vanishing at the point I times 1/2, and this point gives you 1/3. And once you add everything up, well, the contributions from the left and the right side cancel out. The contribution from the top side will give you the order of vanishing at infinity. And the k over 12 comes actually from integrating the d log f over these two arcs. Okay. So once we have this result about zeros, we can check, well, we can prove an upper bound, a very simple upper bound on the dimension of the space of modular forms. So what happens is if...
Excuse me, Danilo, there's a question in the chat. Maybe you want to say a little more about the geometry. The question is how these numbers NZ relate to the covering or this tessellation you showed earlier.
Let me see. Well, I'm not sure which slide it is about. So
it's whether these NZs relate to the ramification in the cover from the half plane to the quotient.
NZs. Oh yeah, sure. Okay, but I'm not, yeah, that's true. So what happens is, okay, let me look at this picture. So what happens is this is third root of unity. And if you take the quotient, you actually get the fundamental domain. I mean, because of the fact that it's stabilized by an element in a PSL to Z, when you take the quotient, you actually get kind of an orbifold point, and that's the size of the stabilizer tells you the full angle there. And it's going to be 2 pi over 3. And that's more or less why we need to introduce this thing. And the same thing happens at the point I, which it's hard to see from here why anything strange should happen, but actually it does. And that there it's going to be an angle, a full angle pi. But I kind of, I was considering talking about the modular curve in these lectures, but somehow I've decided to keep to a very elementary level. So what one can do is one can define the quotient and then study modular forms somehow as sections of some line bundle on the quotient. And then more or less everything, I mean, you can never mention the upper half plane if you do it well enough. But yeah, I prefer to do it a bit more elementary. I'm not sure if this actually answers the question, but hopefully it does. Okay, so so I was here. So I was going to prove you that the space of modular forms of weight k is finite dimensional, but actually, I mean, the proof gives you an upper bound, which is, it depends on the congruent, on the residue of k modulo 12. And the proof is very easy. So we have the condition that the total sum of all orders of zeros of our function is bounded by k over 12. I mean, it's exactly equal to k over 12. In particular, it cannot be more. But on the other hand, if our space has sufficiently large dimension, we can just, by linear algebra, enforce vanishing at any, well, at any number of points. So that would obviously contradict it. But if we do it a bit more carefully, so let's say we have m plus 1 modular forms. And well, m is this number, the same as in the theorem. And then just by linear algebra, you pick some m points in the in the fundamental domain, which are not elliptic. And because you have m plus 1 coefficients, so you just take linear combinations of these, of the modular forms with coefficients c1 up to cm plus 1. Since you have more coefficients than equations, you have at least one solution. And because of the theorem on the total order of vanishing, actually, it shows that it cannot happen because m is strictly greater than k over 12. So all the contributions from that formula are non-negative. And because of that, you get a contradiction. So this proves this upper bound. And in the case when k is congruent to 2 modulo 12, well, there's some funny number theoretical coincidence going on. So if you look at the formula, well, if you write it out, you have some contribution of things with a denominator 3, and some contribution of things with denominator 2, and some integers. But on the right-hand side, you have something which is modulo 1, it's 1/6. And actually, if you try to write 1/6, something which is congruent to 1/6 modulo 1 as a combination of thirds and halves, you have to use at least 2/3 and at least 1/2. And because of that, you kind of overshoot by 1 using elliptic points. So any modular form of weight congruent to 2 modulo 12 has to vanish at least twice at the row and at least once at I. And because of that, the same argument now you get one more. So you get one dimension. The dimension goes down by 1. Okay. So hopefully it's clear. Now there is a nice so for people who prefer more analytic arguments, there's a nice proof which doesn't give necessarily good bounds, but it's easier to generalize to some situations which don't involve necessarily analytic objects. So what, and I give it as an exercise, so it's going to be in a sheet with, which we'll send out, or which we'll put on the website, I guess. But the exercise is, you can obtain the finite dimensionality by, well, first of all, it's enough to look at cusp forms, but moreover, you can actually look at cusp forms and define certain norms in that space. And on that space, well, there are two norms which one can define. So one of them, and the exercise sheet will give a bit more explanation why one looks at this. But this has something to do with Peterson inner product. In any case, one just defines these two norms. So one is like an L2 norm, and the other like L infinity norm with certain weights. And well, these are well defined. I mean, it doesn't matter that you pick a different fundamental domain. So this is, you're really taking this integral over the quotient. And one can actually show, using the fact that f is a modular form, or more precisely that it's a cusp form, that the L infinity norm is bounded by something, some constant times the L2 norm. And whenever you have such a situation for a function space, you actually can prove that it's finite dimensional. That's something, well, I mean, there's something more general, but in particular, in this case, if you take an orthonormal system, you can prove that the number of elements in it is bounded by some constant, which doesn't depend, it only depends on the volume of the fundamental domain and on this constant ck. Okay, so this gives a different proof that the space is finite dimensional. Unfortunately, I don't think one can make it precise to the point that in a moment I will actually prove that the upper bound from the previous slide is optimal. Okay, so we want to show that the upper bounds are actually attained, so that the spaces have exactly the dimensions we wrote, the upper bounds that we wrote before. And for that, we have to compute some non-trivial elements of the spaces modular forms. So, and the way to do it is to compute Eisenstein series. So an Eisenstein series of weight k, as long as k is strictly greater than 2 and even, is defined by the following expression. So you can ignore this factor on the left, which is only there to make things, to make it have a Fourier expansion with rational coefficients. So the important part is this sum. So you sum over all pairs of integers except for the zero vector. You sum 1 over exactly the factor that appears in the definition of modular forms to the power k. So, and the calculation is because for k greater than 2, the thing is absolutely convergent, we can rearrange terms in whatever way we like. So if you plug in, instead of tau, a tau plus b over c tau plus d, you kind of, you just simply pull out the c tau plus d to the k out of the sum, from each term. And then the sum inside is actually, again, the sum over all pairs of integers. Is just under a change of variable, under a change of basis. So if you multiply the vector mn by the matrix ABCD on the right, you get another vector m prime n prime. And this is exactly the sum that appears here. And it's trivial because ABCD has determinant 1, that this actually again runs over all non-zero vectors and non-zero integer vectors of length 2. So because this is again the same sum, this is actually equal to gk of tau. So we get the modular transformation property from this. Okay, so now we can actually compute the expansion explicitly, and for that we have to use the formula, which is in the exercise sheet. So there is this nice formula which is due to Lipschitz, which some of you may have seen in the courses of complex analysis for k equals 1, where you have to care a little bit about how you actually sum this thing on the left. But for k greater than or equal to 2, the sum on the left is absolutely convergent. And so the claim is that this, the sum is actually, you can develop it as a Fourier series in this way. Because, well, the function on the left is obviously translation invariant. Okay, so if you apply it to the sum that we have, so first, maybe I come back. So first of all, you split the thing into 2 parts. So let's say we sum over m. First of all, we have to sum when m is 0, and that gives you a constant term. And when m is positive, well, we get some sum, but for m is negative, it's actually the same sum as for m is positive, which is why I have this 2 here. So if you do it correctly, you get the constant term contributes to this, and the rest of the sum contributes to if you just apply Lipschitz formula, and this factor cancels out with the one that I introduced in the definition of GK. So you get this sum, and you work it out. Well, you have to use the formula of Euler for zeta of k, or actually you can prove it more or less by this Lipschitz formula, that the constant term is actually a rational number, which is the Bernoulli number of the case Bernoulli number divided by 2k with a minus sign. And the rest of the sum is exactly this divisor sum that I've introduced before. So you basically sum L to the k minus 1 over all divisors. So bk, if you don't know what it is, you can just think of it as numbers defined by the following generating series. So it's the Taylor expansion of this function at 0, except, well, you put k factorial in it. Okay, so we have some functions, and now from this formula on the previous slide, we can compute the Fourier expansions. So it's convenient for small indices to normalize Eisenstein series to have constant term 1, which makes it easy to multiply them. Well, at least the first few terms, it's easy to multiply. So the first few functions are written here. And what one notices immediately, well, maybe not immediately, but after some thought, that if you multiply E4 3 times, so if you take E4 cubed, then it has a Fourier expansion starting with 1, and then the second term is 720. And if you take E6 squared, then you get a Fourier expansion starting with 1, and it has minus 1008, the second term. So in particular, these two functions are linearly independent. So already for the dimension, the space of modular forms of weight k, of weight 12, you get two linearly independent functions from here. And actually, if you look at the slide where I gave the inequality, it actually is the same as the upper bound for the dimension. So at least in weight 12, we get everything. But actually, one can prove that if you take any polynomials in E4 and E6, you recover the full space of modular forms, so the full ring of modular forms for PSL2Z. And the main part in proving this is to prove that these two things are, these two modular forms are algebraically independent. So I will say why this is enough in a moment. But first, let's see why they're algebraically independent. So we know that these two forms, E4 cubed and E6 squared, are linearly independent. It turns out that this is actually enough. So first of all, to show that E4 and E6 are algebraically independent, it's enough to do it for E4 cubed and E6 squared. And next, so if you have some polynomial which kills E4, which vanishes on E4 cubed tau and E6 squared tau in two variables, then we may assume, if you look at the transformation of this, of the left-hand side, when you plug gamma tau instead of tau, you see that different homogeneous components of this expression actually produce different factors. So if you group them by the homogeneous, if you look at each individual homogeneous component and you apply sufficiently many gammas, you actually obtain that all of them should vanish individually. So then it means that we may assume that if there is such a polynomial, we may assume it to be homogeneous. But if it is homogeneous, well, what does it say? I mean, any polynomial, any homogeneous polynomial in two variables, it essentially has finitely many solutions in the sense that if you look at ratios of the two variables where it vanishes, this is a finite set. But we already know that E4 cubed divided by E6 squared is not a constant because we showed that these two functions are not linearly dependent. And so this implies that they're actually not algebraically, they're algebraically independent. Okay, so now that we have this, we can actually prove that the full ring of modular forms is simply can be written as polynomials in the two Eisenstein series, E4 and E6. And why is that? Well, we had the upper bound, and then there is a combinatorial calculation. So if you try to write up as many monomials as you can in E4 and E6 of weight k, then you have to calculate this number. And it turns out that it's actually equal to the dimension bound. And if k is not if k is congruent to 2 modulo 12, it's also equal to the dimension bound. So in all cases, in all cases it is equal. And then we get that because we have an upper bound, which is given by this number or this number, and now we have a lower bound because we have this many functions just among given by monomials in the E4 and E6. So this shows that these two bounds match, and actually this means that this is the full space of modular forms of weight k. All right, so I want to say a few things about the Eisenstein series of weight 2, which I mentioned in the first lecture. So one can simply imitate the definition of gk for higher k. We had this, sorry, the definition we can't imitate, but we can imitate the computation of the Fourier expansion, which if you do it for just naively substitute k to be 2, we would get this function. Now what happens is that this function doesn't quite transform like a modular form, but it almost does. And that will be important in the last lecture when I talk about the applications to sphere packing. Like one thing which is maybe not immediately clear from this Formula 1 is actually, again, it's enough to check this identity only for the generators of the group. So it's again something I leave as an exercise. And then, well, once we know this, it means we actually have to prove the identity only for the generator S, because since the function itself is given by a Q expansion, it's already periodic automatically. So there are actually two ways, well, there are more than two ways, but I'll mention two ways of proving that G2 does satisfy this property, the transformation law. So one is the so-called Hackett trick, and it's actually, I won't go into details, but it's something very useful in many situations. So what you do is you had the issue, the only issue is the proof that we used for GK when K was greater than 2, that appeared when K is 2, is that we no longer have absolute convergence. So we can rearrange the terms of the series in whichever way we want. But we can recover back the absolute convergence by introducing this small factor here. And now this object G2 epsilon of tau, it's easy to see by the same proof as before, it has a certain modular type transformation property. And then the only thing that's left is to connect it to the G2 of tau we have. And this is accomplished by this limit formula. So one can prove that this limit is almost G2 of tau plus some correction term. And then using the transformation law, which is easy to prove, we recover a transformation law for this object, which turns out to be equivalent to the one I wrote before. Okay. So there's another proof, which might look kind of awkward, but it also leads to some interesting ideas. So that is, well, we only need to check the transformation law for S. And for that, we need to verify this identity here. So and it's actually enough to verify it for for Y on the real line, for positive real Y, because everything else is recovered by uniqueness principle. And so what we do is actually something I'll talk a little bit about later. We associate to G2 the following L series. I mean, it's an L series with the gamma factor together included. So we integrate G2 of IY plus the constant term, so we want to kill it off, times y to the s minus 1 from 0 to infinity. So if you know, this is, if you've seen it before, this is the Mellin transform of this function. And just integrating the Fourier expansion, we get that this is this sum. So it's 2 pi to the power minus s times gamma s times the Dirichlet series for the divisor sum function. But actually, well, it's again a simple exercise. This Dirichlet series for the divisor sum function is the convolution of the, I mean, it's a Dirichlet convolution, so you can actually compute it. It's the product of zeta of s times zeta of s minus 1. So now we have this, and it turns out there's a way to go between the transformation laws of type 2 and functional equations for L series like this. And in particular, in this case, well, using the functional equation for the Riemann zeta, we can prove that L of 2 minus s is minus L of s, just by plugging, I mean, just by using the functional equation and the duplication formula for gamma. And then once we know this, and also that L has only simple poles as points 0, 1, and 2, with residues we can easily compute. This allows you to recover 2 by applying inverse Mellin transform. Okay, so it might seem a little bit too technical, but it's actually, I mean, this trick happens more often than you might think. I mean, it's more useful than you might think. Okay, so why did I bother with G2 at all? Well, one of the simplest applications of this, of the Eisenstein series of weight 2, is that we can prove that the modular discriminant function is actually modular. So the function given by this infinite product, so you take Q times the product written here, is in fact the cusp form of weight 12. And so the way to prove it is, well, it's hard to work directly with products, but if you think about, well, what you can do is you can take a logarithm, and well, it's sometimes useful to differentiate logarithms because then it's still given by rational series in rational functions of Q. So what you do is, well, if you just do exactly what I said, if you take the logarithmic derivative of delta, you get this series, 1 minus 24 times this sum. And actually, if you think a little bit about it, it's exactly the same as what would be an E2. So it's exactly the generating series for divisor sums, if you just expand this 1 minus q to the n in the denominator. So, and now what you do is you apply the functional equation for E2, which reads in this way. And this tells you that the logarithm of delta transforms, or the derivative of logarithm of delta transforms a certain way. And then if you integrate it once, you get that the logarithm of delta transforms in a certain way with maybe some constant. And that transformation law is exactly this. And then the constant, you can determine the constant by just specializing this identity to tau equals I. Because then on both sides you get the same number. Well, delta is the same, but C should be 1 then. Okay, and well, you know that delta is not, delta doesn't vanish at I because it's, you can work it out from here. Okay, so I'm running a little bit over time, but I just want to mention a little bit about delta. So the space S12, if you look at the dimension formula, it's one-dimensional, and well, we have delta from the previous slide, but we also can write this combination in E4 and E6. And because the space is one-dimensional, these should agree up to constant, which is 1728. And well, one reason why delta is, delta is a very important function, but one of the reasons is that, well, you can define the modular J invariant using it. And the main reason why this is a nice object is because delta doesn't vanish anywhere in the upper half plane. But the delta function itself is probably a lot more interesting. And what is a famous observation by Ramanujan, if you look at the coefficients of this Q expansion, which there's a terrible clash of notation, but I hope you don't mind. So this tau is the same as, it's not the same as this tau. This is just a sequence of numbers. And he looked at this sequence, and he has noted that, well, first, that this was multiplicative. And second, that if you look only at primes, then these coefficients are actually quite small. Well, relatively speaking. So what he explicitly noted that this inequality always seems to be holding. And well, one of the claims, the multiplicativity, was resolved next year by Mordell. But the other claim turned out to be much, much deeper. It actually had to wait until 1974, yeah, when Deligne proved Weil conjectures. And then he used the result of a few years before then, when he reduced this conjecture to a special case of Weil conjectures. So it's a lot deeper stuff. Okay, maybe I think I should stop.
Thank you very much, Danylo.